So by this point, we've discussed many of the state variables of thermodynamic systems, these gases, both macroscopically in terms of how they were historically understood, and microscopically in terms of the kinetic theory of gases. But now it's time to talk about how exactly they relate. And they are connected through something known as the gas laws. Eventually, though, we will also get to what are known as PV diagrams. So as you recall, these state variables can change through time. So originally, our thermodynamic system, our gas, is in some initial state with some initial pressure, initial volume, and initial temperature. But this can change as various factors are altered. And we can go to some final state, we'll say A, with pressure PA, volume VA, and temperature TA. But that's not the only option. There are literally limitless numbers of states we can go to, and we have to be able to figure out, well, how do we get from one to the next? Well, the first way to do that is establish how exactly these different variables are very specifically related to one another. So let's look at the first of these relationships. Imagine we have two boxes here filled with gases that are at different temperatures. This top one is a gas at a very low temperature, so the molecules are, on average, moving fairly slowly. They have a low amount of kinetic energy. And the box at the bottom is at a relatively high temperature. So on average, the molecules are moving much faster, have much more kinetic energy. Well, if we look at the top box, the cold one, if we look at one of these molecules here, when it strikes the wall, keep in mind these are always going to undergo elastic collisions with no loss of energy. So therefore, the kinetic energy of these particles are going to be conserved when they impact the walls of the container. So if I look here, I have my molecule. It goes with some velocity v naught, hits the wall of the container, and then bounces back with a new velocity v, which is the same magnitude, but opposite in direction. Now recall that that means this molecule has undergone some change in momentum or impulse equal to m delta v, which we also know is equal to F delta T, where F is the force of the container on the molecule, and delta T is the time of that interaction. Now if we look down at the bottom box, with the one that's high temperature, we can look at a molecule that is moving at a much higher average speed, and well, there's going to be a much bigger change in V. So we have delta P is equal to m, but delta V is going to be much, much bigger now because the molecule's velocity going from its original direction to its final direction is a much bigger delta V than in the colder situation. Well, that's going to equal to F delta T. Well, the delta T, at the time that it impacts the wall, is not going to change that much. But this is going to result in a much bigger force. So since it undergoes a greater change in velocity, a greater force must have been subjected to it. And we know from Newton's third law that whatever the force is on the molecule, that's the same thing as the force on the container. And if we have a greater force on the container, that means we're going to have a greater pressure. And this brings us to our first gas law relation, which we're just going to call gas law number one. It actually does have a specific name. I believe it is called the Guy-Lussac law, though I will be honest, I'm not 100% sure of the pronunciation of that. But if the volume of a container is constant, the pressure is going to be proportional to the temperature, meaning that if we have more pressure or more temperature, the other one is going to go up as well. If we have a lower temperature, we're going to have a lower pressure. These two variables are directly proportional. So let's now imagine we have a box filled with a gas with fairly average temperature, fairly average kinetic energy of the molecules. Okay, it has some volume that we don't necessarily know, but let's now make one with a much tinier volume. So we've shrunk the box, but this is really, really key. We want the temperature to be constant. We want to keep T constant, which means we need the average kinetic energy of all these particles to be equal to the average kinetic energy of all these particles. So they ought to be moving, all the particles should be moving at relatively the same sort of speeds. Well, if we look, though, that since this is in a smaller volume, it has way less distance to cover to get from one wall to the other, these molecules do, than over in this situation. And if that's the case, we're going to have way more collisions per unit time between the walls of the container and the individual particles. Well, if we have way more collisions, that means the pressure is going up as the volume is going down. And this brings us to the second of the gas laws, called Boyle's law, which is that if the temperature is constant, pressure is proportional to the inverse of velocity, where P is proportional to 1 over V. So in other words, if the pressure goes up, that means we must be corresponding to a lower volume. As the volume goes up, that means we're corresponding to a lower pressure. So now let's imagine we once again have a box, and it is filled with a gas at a fairly average temperature. And we are going to expand the volume of the box. But we want the pressure between the first box and the second box to be constant. Well, this kind of goes with what we were just talking about. If we look between the small box and the big box, if we want this box to have as many collisions with the walls of the container between all the molecules per unit time as we have collisions between the gas molecules and all the walls of the container with this bigger box, well, that means the bigger box must have molecules that are moving much faster because they have to cover a much greater distance to collide the walls compared to the tinier box. So, as the volume has expanded, and we want the pressure to be constant, we want the molecules to go faster, so the temperature must be going up. And this takes us to our third gas law, often known as Charles's law, which is that if the pressure is constant, volume is proportional to temperature. Meaning that as volume goes up, temperature goes up. As temperature goes down, volume goes down. Now this last relation we're going to look at is a little bit different. Imagine once again we have our box with our gas inside of it with the particles moving at some average kinetic energy, some fairly average temperature. And let's say we expand the volume of the box. So the volume has gone up. We want the temperature to be constant. And we also want the pressure to be constant. So I can't speed up these particles. If I speed them up, the temperature goes up. Well then how can I increase the number of collisions between the molecules and the inside of the box if I can't allow them to go any faster? Well, I simply add more molecules. I increase what we now label as capital N, which is the number of molecules. And this is the final individual gas relation we want to know, or gas law number 4, also known as Avogadro's law. If the pressure and the temperature are constant, the volume is proportional to the number of molecules inside the container. So as we have a larger volume, we're going to have more molecules. And if you have fewer molecules, you have to have a smaller volume. So at this point, we've established 4 different proportionality relationships between state variables of a thermodynamic system of gas. First off, I have what is known as Gay-Lussac's law, that the pressure is proportional directly to the temperature. We have Boyle's law, that the pressure is inversely proportional to the volume. We have Charles's law, that the volume is directly proportional to the temperature. And we have Avogadro's law, that the volume is proportional to the number of molecules. But that's a lot. Is there some way we can combine these all together into something that's way more useful? And many of you probably have an idea of the direction we're going. But we're going to take a little bit of a detour to get there. So first off, let's combine all these into one single proportionality. So I start off with P is proportional to T. That gets rid of Gay-Lussac's law. Additionally, let's say P is inversely proportional to the volume. That gets rid of Boyle's law. Now, okay, let's go ahead and simplify this a little bit. Let's multiply V across. So I have PV is proportional to T. So now we don't need to worry about this. And now I look, V is proportional to T. That gets rid of Charles's law. And now I have Avogadro's law. So this means PV is proportional to NT. And don't have to worry about that one anymore. But this is only proportionality. I want to make this proportionality here an equal sign. Well, how do I do that? To make that an equal sign, I need to figure out what constant times these variables will give me directly these 2 variables. And we are going to label that constant something that you may not be used to, which is PV is equal to N, and the constant we're going to use is K little b times T. And this is something we most definitely need to know. This is actually a form of the ideal gas law. Now, I know you're probably thinking to yourself, well, wait a second, Mr. Varvier, I learned the ideal gas law as PIV-NERT, PV equals nRT. Well, go with me for a second. We have P times V equals capital N, where N is the number of molecules, times KB times T, the temperature. And what exactly is KB is what we call Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. Okay, but this is the key here. This was in molecules. And if you remember from your chemistry class, you learned about little n, not big N, which was the number of moles. Well, what is a mole? A mole is just a humongous number of molecules, specifically 6.02 times 10 to the 23 molecules, which is Avogadro's number, which we're abbreviating here with a capital N and then an A subscript. So if I have 6.02 times 10 to the 23 molecules, so I put that in right here, and I divide it by Avogadro's number, well, a number divided by itself would be 1, so that would be 1 mole of molecules. If I had double this amount, so 12.04 times 10 to the 23 molecules divided by Avogadro's number, I would have 2 moles. So it's just a way to categorize a humongous number of molecules. But let's now get this law in terms of moles rather than in terms of molecules. So let's rewrite this again. I have PV is equal to N KBT, and I am going to plug in for the number of molecules, the number of moles times Avogadro's number. I'm going to multiply that across. So I'm going to get PV is equal to N times Avogadro's number times KBT. I'm going to simplify this, well, not really simplify, adjust it a little bit. I'm going to pull the N out. Now I'm going to put NKB in parentheses. You might be wondering, well, Mr. Varvier, what was the point of that? Well, this is a constant, right? This is Avogadro's number. KB is also a constant, which is the Boltzmann constant. And if I take out my handy-dandy calculator, and I multiply Avogadro's number by Boltzmann's constant, 1.838 times e to the negative 23, I get 8.3076, which rounds off to about 8.31. And that might look familiar to you because we know that as a different constant, the constant R. So now we actually have two different forms of the ideal gas law. One that's kind of a microscopic form, where we are considering the number of molecules, and one that is a macroscopic form, where we're considering the number of moles. So for both of these, I have P the pressure in pascals, I have V the volume in meters cubed, and I have the temperature in Kelvin. You always have to have these in these units for this to work properly. I have Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin, and I have the universal gas constant, which is 8.31 joules per mole times Kelvin. Capital N is the number of molecules, lowercase n is the number of moles. And this is for one particular state of a particular gas, meaning that if I have some gas, and I know the number of molecules, and I know Boltzmann's constant, let's say I know its temperature, its current temperature, and its current volume, then I can solve for its current pressure. Or let's say I know its current pressure and current volume, I know the number of moles, well then I can solve for its current temperature. So let's take a minute to look at an example. Imagine I have some piston over here, and inside this piston there's a gas, and we know all of its state variables. We know its current pressure is 1 times 10 to the 5th pascals, we know its current temperature is 298 K, and we know that its current volume is 1.0 meters cubed. And let's say we then compress it, we push the piston closed. And when we do that, the volume goes down to 0.4 meters cubed, the temperature goes up to 350 K, or Kelvin. Well, what is the new pressure going to be? And we know for a fact the pressure is going to go up. Why do we know that? Because since the volume went down, the pressure has to go up, and since the temperature went up, that also means the pressure had to go up. But how exactly would we solve for it? Go ahead and pause the video, try it on your own, and then come back and let's check in and see how you did. Hopefully you actually tried it, but I'm going to first I need to solve for the number of moles, or I could have equally have solved for the number of molecules. Either one is fine. I'm going to go ahead and stick with the equation that most of you know, which is PV equals nRT. So I'm going to use that over here in this left-hand example, and I'm going to stick in P, V, and T. R is a constant, so we can solve for N, the number of moles. So I go ahead and rearrange this equation to solve for N. I stick in all of these different values. Remember R, we have to use the number 8.31. There are other versions of R. We are always going to stick with 8.31. And when we do this, we get that there are 40.38 moles in this piston. Well, those moles aren't going to change over here. We know that there must also be 40.38 moles when we've compressed it even more. So now I can do PV equals nRT again, and this time solve for the pressure. So I just divide both sides by V, and I stick in N, R, T, and V with my new T and V values, and I get a final pressure that, okay, this is way too many sig figs, so we're going to kind of cut it off a little bit. I get about 2.94 times 10 to the 5th pascals. Indeed, the pressure did go up. But there's something I want you to notice here. We had to kind of take this weird middle step where we had to solve for the moles before I could go over here and solve for the new state. Is there a way I could skip that step and therefore immediately go from these variables to these variables? And in fact, there is a way to do it. So let's imagine we have some sample of gas, and initially it's in some state, state 1, with some pressure, some volume, and some temperature. But we can adjust this gas so it enters into a new state, state 2, with a new pressure, a new volume, and a new temperature. Well, how could we easily go between these two? Well, we can, as long as we recognize that if it's the same sample, we mean there's going to be the same number of moles or molecules. So we need to make sure this gas is sealed. We need to make sure it is sealed inside of a piston so that none of it escapes. The number of moles or molecules stays the same. So let's write now the ideal gas law for both of these. So I could say this is P1 V1 equals nRT1. Now I could say over here P2 V2 equals nRT2. Well, let's rearrange this to find N and R. So I'm going to have P1 V1 over T1, just divide that across, is equal to nR. And similarly, I have P2 V2 over T2 is equal to nR. But let's notice something. R is a constant. And N is a number of moles. As long as it's sealed, that should also be the same. So we can equate this part with this part and get one single relation to quickly move from one state of a gas to another. This is called the combined gas law, and it is an extremely, extremely useful relation. I have the state of gas in one particular state with one pressure, one volume, and one temperature, and then I can quickly move to another state of the gas with the same pressure, with a different pressure, volume, and temperature, as long as I know a couple of factors of the new state. So we can compare different states of a gas as long as the gas remains sealed and the amount of gas remains constant. So we're going to finish much of our discussion today with what are known as PV diagrams. A PV diagram is simply a graph. It's a graph that allows us to visualize changes to the state of a gas. So let's make sure we know this is basically a graph. And it's going to be a graph of pressure versus volume. You'll notice volume is on the horizontal axis because it is independent. We typically adjust the volume. We either cause a piston to increase in size or decrease in size, and that will in turn change the pressure. And I also want you to note the units here. The pressure here are in terms of times 10 to the 5th pascals, meaning this is 1 times 10 to the 5th, 2 times 10 to the 5th, 3 times 10 to the 5th. That is very, very common, so you need to get used to seeing that. Every state on here, every point, is equal to a particular unique state of a gas. Because if I look at PV equals nRT, if I have some combination of PV, let's pick this point here, Well, that means that as long as I have no P and V, I can figure out the temperature as long as I know the number of moles or the number of molecules. But if I go to a different location, like over here, well, now I have a new pressure, I have a new volume, and I very well could have a new temperature. So let's look at this a little more detailed, though. Let's say, for instance, I start at this point right here in the middle. Well, if I move upward, my P is going to go up, right? The pressure increases, but the volume stays the same. But if the pressure increases and the volume stays the same, that means the temperature must also be increasing. Well, now let's look here. If I go this direction, I have the volume increasing, but the pressure stays the same. But if this goes up, this stays the same. Temperature, once again, has to go up. Let's go the other direction. Let's say I go from here this way, and now the volume is decreasing, the pressure stays the same, so now temperature goes down. And if I go downward from this point, the volume stays the same, but the pressure decreases, so the temperature decreases. In fact, this can go a little bit further. If I increase both the pressure and the volume, well, okay, if we are increasing both of these, we know for a fact temperature is definitely going up. And if we go in the opposite direction, we decrease both of them, we know for a fact that the temperature is going down. However, and I'm going to actually change the color here, this one and this one are kind of mysteries. We have to be a little more specific with our calculations, because pressure and volume, if they are moving back and forth past each other, they could cancel each other out. It depends on what specifically we're looking at. So let's give an example to talk about this in a little bit more detail. Imagine we have some sample of sealed gas, and it undergoes a thermodynamic process from state A to state B. So on this PV diagram, we go from state A, and it's going to change to state B. Now you'll notice, if we looked at the previous slide right here, we don't necessarily know if that means the temperature is going to go up or down. So instead, we know that in state A it says the temperature is going to be 200 Kelvin. We know that the pressure is 2 times 10 to the 5th pascals. We know that the volume is 0.5 meters cubed. If we look over here, we have a pressure of 1.5 times 10 to the 5th pascals, a volume of 1.5 meters cubed. What is this new temperature going to be? Now you can probably figure this out. You could use PivNert in this first situation, PV equals nRT, solve for the number of moles, stick that back into here. That's going to waste your time. Instead, let's go directly from one state to another with the combined gas law. Now, I specifically am looking for the temperature at point B, so I need to solve for this one. So I'm going to cross multiply and then divide both sides by PAVA. And when When I do that, I get this equation here. So now I just stick in all the numbers. The temperature at A was 200 Kelvin. The pressure at B was 1.5 times 10 to the 5th pascals. The volume at B is 1.5 meters cubed. The pressure at A was 2 times 10 to the 5th pascals. The volume at A was 0.5 meters cubed. You stick these into your calculator, and you get a temperature of 450 Kelvin. The temperature, in fact, went up. And that actually makes sense, because if we look here, the volume increased in size. So this was my original volume. It doubled. The volume tripled, but the pressure, which was originally here, didn't even go down by half. So the change in volume was way bigger than the change in pressure, and that increase in volume therefore necessitates a very big increase in temperature. So what are the takeaways here of gas laws and PV diagrams? Well, right now we want to make sure we can conceptually relate how the state variables, temperature, volume, and pressure, can relate with each other as they change. Additionally, we want to utilize the macroscopic and microscopic, the macroscopic being PV equals nRT, the microscopic being PV equals capital N times kBT, versions of the ideal gas law. We want to be able to utilize the combined gas law and save ourselves some time. And lastly, we want to be able to interpret basic PV diagrams. Be able to quickly tell if a gas is changing, is its temperature going up, going down, or do we need to look at it a little more carefully?